Well, the title here for my presentation is Soil Basics, but maybe not quite so basic. It depends on what you mean by basic. Basic does not necessarily mean elementary, but it means sort of the fundamental levels of what we need to understand about soils. So I've taken a little bit of a different approach, but before I do that, I wanted to mention that we've just finished a book on the modeling and design of flexible pavement systems, published by Springer, and it goes from the chemistry and the basics of the asphalt to the mixture, through the aggregates, and then to the mechanics of flexible pavement design. So just let you know that that book is available now through Springer. My co-authors there are David Allen, who's on the faculty here at A&M and also in TTI, and Amit Bhasin, who's the associate professor over at UT Austin. So a little bit of an outline of what we'll talk about today. I want to talk about where you can find some basic information on soils. Secondly, I want to go over some basic structure of soils that helps us understand how they behave. And then finally, I want to focus on the clay minerals, and in term specifically the volumetric instability and why it is unstable from a volumetric standpoint. And then finally, if we have time, and I'll look for the cue as to whether or not we have time for all of these, I want to talk a little bit about how understanding some of these basic principles of soils can help us understand what happens when we add an amendment to these soils, such as Portland cement or hydrated lime or quicklime, fly ash, or even some of the non-traditional stabilizers, such as the injectable solutions that are acidic, basically, or they're acidic in nature. I don't say basically acidic, because that's counteracting the acidity right there. Might get a salt out of that, but soils are amendments that have an acid basis to them, is what I'm trying to get to. And then finally, polymers are coming on the market as a stabilizer for these soils, so we'll talk a little bit about how the polymer systems might be effective stabilizers as well, and how we can understand that mechanism based on these fundamental properties of soils. To begin with, an excellent resource for information on soils would be the National Conservation Service County Soil Reports. Now, these reports have been around a long time. They just used to be just called the Department of Agriculture Soil Reports, and now they're called the National Resource Conservation Service Soil Reports. These reports give you a wealth of information. Within each county in the state of Texas, there is a soil report, and in that report you'll find all of the information that you can imagine on Atterberg limits, the basic chemistry of the soils, and you'll also find some healthy information here on the soil profile. This tells you, first of all, what the parent material is, and knowing the parent material, it will help you understand the basic chemistry, if you're into that, of the soil. You'll be able to determine approximately what the depth of the organic containing zone is, which we call the A horizon. And then the B horizon would be the horizon that is where some of the leaching of some of the rich minerals occurs. So these minerals are leached out of the upper part of the B horizon, and they're captured in the lower part of the B horizon, which makes it a very fertile portion of the horizon for stabilization, because these materials have gone through a weathering process, making them more active when we add something like lime or cement to them in the terms of the pozzolanic reactions. We can also figure out from these county soil surveys whether or not we have sulfates. And sulfates, as you know from experience and from general knowledge, can interrupt the stabilization process, particularly with calcium-based stabilizers. this is the corridor for State Highway 130. And just taking that as an example, these are some of the soil series that you would have to go through in that corridor. So in the county soil reports, you would find excellent data on all of those soils, including the profiles, including Atterberg limits, including potential swell properties and strength properties. So excellent source of information. Now, we said we're going to get into some basics, and I wanted to start with one of the most abundant of all soils, and that is a silica-based soil. So the silica-based soils are made up of oxygen and silicon that are coordinated in this tetrahedral type of an arrangement. And if we have a crystalline form of the silica, it's extremely stable. And crystalline simply means that it has close range order and it repeats itself, and that long range order is established as well. So by knowing the basic unit cell of that material, we can expand that and understand what the properties are overall of that particular soil. And it's very, very stable. A crystalline material is stable. And the reason it's stable is because it has a low free energy. And nature wants everything to have a low free energy. That's the stable state. If we come out and look at the way the silica can organize themselves, in which the free energy is greater, such as this, we call that non-crystalline because it does not maintain that long-range order. And it's much less stable. And here's another example of a soda silica glass, which contains the sodium ion in the structure. Very unstable. Picture of quartz right there, quartz crystal. When molten material solidifies, it goes through a cooling process. So this is temperature, and here's the melt temperature up here. So as the temperature decreases as it cools, if that occurs at a rapid rate, then there's not enough time for those basic building blocks to organize themselves in a low energy state. Not enough time. So they are disordered. They're amorphous. On the other hand, if the cooling rate is slow enough, then they can ultimately lock themselves into position, coordinating to positions that lower their free energy and making them crystalline in nature. And if you compare the difference between the rapid cooling and the slow cooling, you can see that there's an excess of volume in the rapid cool over the slow cooled. And that is directly related to the instability of the material. Now, why do I talk about that? Because, for example, if you're using a sand material in concrete, and that sandy material happens to be crystalline in nature, then the probability of, in the high pH environment, that crystalline quartz-type material, the probability of having it break down and forming an alkali-silica reaction is very low. On the other hand, if the silica-based sand that you're using has a high free energy because of rapid cooling, for example, and is amorphous in nature, then the probability for that to react in the high pH environment, pH about 13 or so, where silica is quite soluble, is high. So that's a reactive material. And it's reactive based on this principle, that the crystalline material cools slowly, it forms the bonds that are needed to lower its free energy. The amorphous material, which is cooled rapidly, is not as well organized. It has incomplete bonds. It has a higher free energy. Nature wants to reduce the free energy, and at that high pH environment, it will be soluble and react to lower its free energy. So here's a picture of something that all of you are somewhat familiar with, and that is what happens when you have an alkali-silica reaction because you have an unstable or amorphous form of silica. and in the high pH environment it reacts, it becomes soluble, and forms a silica gel, which expands over time and can be very harmful to the product, to the concrete product. Okay, now from there I want to go into the clay minerals, and I've got some very pretty slides. They're kind of complex looking, but the idea here is that the basic building units for clay are made up of, well, let's take a look at them. These pyramid-looking systems are silicon and oxygen. The three most abundant elements in the Earth's crust are oxygen, silicon, and aluminum. So clay minerals are made up of those elements. And these little yellow pyramids are the silicon and oxygen basic building blocks. The green here would be the aluminum and oxygen building blocks. So I've got a layer of the silica tetrahedra, and I've got a layer of the aluminum octahedral layers. I say octahedral because there are 8 sides here, there are 4 sides up here. Tetra 4, octa 8. And so they bond together in these sheets. Kaolinite, an individual sheet of kaolinite is linked to another sheet of kaolinite by hydrogen bonding, which is pretty strong secondary bonding. So the form of kaolinite turns out to be, if you look at it through a microscope, magnified maybe 1,500 times, it looks like this. It looks like stacks of hexagonal particles. But the idea here is that the clay particles are plate-like, and they have a high surface area. Kaolinite is not really a problematic clay. It doesn't swell very much because it has fairly strong hydrogen bonding between the plates. So that would be an individual plate. Another one would repeat itself down here and would have hydrogen bonding between the plates. Pretty strong bonding. Won't break it very easily. Then we move over to the real problem, the smectite clays. So once again, these smectite clays are composed of layers. In this case, here's the silica tetrahedral layers. You can see the silicon, the purple in the middle, the oxygen, the blue on the outside. We got a layer up here, a layer with peaks pointing up down here, and in the middle you've got your aluminum octahedral layer. So you've got these materials that are composed of oxygen, silicon, and aluminum, the 3 most abundant elements in the crust of the Earth by far. So it's no surprise that they comprise these structures for clays. The idea here, though, is that they're plate-like. And the other idea that I'd like to pose to you is that they're extremely small. They're micron size. Now, one thing that you remember from your basic schooling somewhere along the way is that when you make something smaller, you increase the surface area. So clay is many times, orders of magnitude smaller than silt. And that makes it very high in surface area. So if you look over here to the right-hand side and you see the silica, oxygen, and silica layers, and then you see another basic stack of those layers, or another particle of clay, you can see that the clay is bonded, or these basic layers are bound together by these blue or purple circles, which are cations, positively charged atoms. And the reason for that is that because of nature does some substituting within the clay layers, the clay surface is strongly negatively charged. So it attracts positively charged particles here to its surface, like sodium or calcium or magnesium or potassium. And those positively charged particles try to neutralize that negative charge. In addition to that, those positively charged particles, as you see right here, hydrate. They attract water. And right here I've got depicted the water molecule. If you can see it, it's a little bit hard to see, but you can see the big white circle, that's oxygen. And the little blue circles, those are 2 hydrogens, and they look like little Mickey Mouse ears. So you got the positives on one side, you got the negative on the other, so water's like a little dipole magnet. And it's attracted to that positively charged atom. So suppose that positively charged atom is sodium. In other words, I've got a smectite clay that is saturated with sodium. What can we say about that smectite clay? We may spend most of our time talking about this slide. If we do, that's fine. But this is a very important point. What happens if this very, very small structure, micron in size, very high surface area, with a surface that's negatively charged because of substitution within the sheets itself, what happens if it is saturated with sodium? Well, what happens is that there can build up a very, very large layer of interstitial water between the individual particles, the individual layers. And that water, as it builds up, weakens the clay structure. As the water is pulled out by certain environmental conditions, the clay dries, the particles come closer together, and it hardens. Now, the size of that interstitial water layer is going to depend on the cation that's available. If I were to add Portland cement or lime to that clay system, the dominating cation would be calcium, which has two charges, two pluses to it. And calcium does not hydrate at the same level as sodium does, so it would suppress that water layer. It would reduce the shrink and swell characteristics of that clay because it's saturated with calcium instead of sodium, and give it a lower plasticity index, give it less potential to swell, give it less potential to shrink, improve its volumetric stability. So hopefully you can kind of glean that from this particular picture. Now, with a little animation, I can just show you another picture. Let's suppose that purple atom there is sodium, and in this case I color it gray. And this just shows you a little bit better picture of the positively charged sodium atom attracting the negative sides of the red oxygens, and the positive hydrogens are out here. So it's like little magnets, and it's pulled to that sodium. Sodium has a huge hydrating potential. That's why you lower your sodium if you have high blood pressure, because you don't want it to hold all that water within your system and increase your blood pressure. Okay, this is down here a picture of an electron micrograph of the smectite clay. Magnified, I'd say maybe 2,500 times, but you can see the plate-like structure of the clay as it continues to show itself. And then over on the right-hand side, you see this same system where it has been subjected to a drying operation, and the water has been sucked out of the interstitial areas and the interstices of the clay structure. So it collapses like an accordion. And there you can see the shrink-swell mechanism. You can picture the instability. This is what happens under desiccation, and if I feed this with a water source, the layers rehydrate, as we've talked about here, and they're pushed apart, and they form this type of a structure. So this would be the swollen structure, this would be the desiccated structure. So now we have a good picture, a good basic picture of why clays swell and why clays shrink, why they're volumetrically unstable. Here's another picture. This is from a book by Dr. Wilding of the soil science here at Texas A&M. He did this years ago looking at vertisols. We have vertisols all over Texas. And he just shows the extreme change in the microstructure of clay. This is fully hydrated where the layers are pushed apart because of that water that's held interstitially. And then as we apply suction to it, you can see that those layers collapse, and more suction collapses even further. So there's your swell mechanism. So let's talk a little bit about what might happen to these clays if we add some type of a calcium-based stabilizer. Now this could be lime. Of course, lime, what is lime? Lime is calcium oxide. And if you hydrate lime, it's calcium hydroxide. It holds about 25–30% water when you hydrate it in hydrate form. When you add lime to water, there is some dissociation of the lime in the water. And the hydroxide ions make the pH go way up to about 12.4 at room temperature. High pH, very basic condition. The calcium is released from that molecular structure, and so you have this calcium with two charges, two positively charges, that's floating around and can be attracted to that negative clay surface. And because it has two positive charges, it will suppress that interstitial water layer, making it less volumetrically active, more volumetrically stable. Cement can do the same thing. Now, they do it to a little bit of a different degree, but cement has free lime in it as well. And it's your choice to which one you choose to use there. But this is actually a transmission electron micrograph that illustrates that point. The transmission electron micrograph here is showing a clay system. And the one up here at A is saturated with sodium. The one down here at B is saturated with calcium. And you can see that the calcium saturated system is darker and more dense, which means that the clay layers are stacked more closely together because of that satisfying nature of the calcium for that negative surface charge. It's satisfying that negative charge and suppressing the amount of water that can be held. And also the calcium hydrates to a much lower degree than the sodium does, so less interstitial water. And up here, of course, the interstitial water is sodium saturated and the clay layers are pushed apart. This gives you some illustration of the actual thickness in angstroms, which is just a unit of measure, 10 to the minus 9 meters. You can see the distance between the individual layers, which is much greater here in the sodium saturated system than in the calcium saturated system. So when I add cement or lime, which is a calcium-based stabilizer, when I add that to a soil, a clay soil, I'm saturating that clay with calcium. The calcium is suppressing the double water layers. It's making these tectoids, which is an agglomeration of the individual plates to form particles. It's making them stiffer and stronger. So immediately the clay has gained stiffness. It's become a higher modulus. It's gained strength. It has a higher shear strength, and it's volumetrically more stable because of the addition of the calcium-based stabilizer. So at this point, hopefully, in terms of our soil basics that are not quite so basic, you understand what the clay looks like. And let's review it. The clay is a plate-like particle that is composed of layers of silica and oxygen, aluminum and oxygen. And there's some substitution within that matrix that makes the surface negative. And the particles have a very, very high surface area. So the composition, including the high surface area, the high charge density at the surface, makes it readily available to attract some type of a particle. And those particles are sodium, potassium, magnesium, calcium. The ones that have the 2+ charge are going to do a much better job of suppressing the amount of water that can be held. And the result of that is to reduce the swell potential and to improve the Atterberg limit properties and then to improve strength. So that's kind of the review of what we've talked about with these clay materials. Let's see. Now here's an illustration of what can happen to these clays when we add, in this case, lime. This is an actual reconstruction of a roadway where here in central Texas, or in Texas, south of Austin, where the lime stabilized layer has been ripped out to extend the lime stabilized layer. And this was after about 4 months being in place. The compressive strength here was somewhere around 300 psi. The natural soil compressive strength is about 30, so that's a tenfold increase in compressive strength. And the next slide down here, you can see the natural soil down here, which you can see the desiccation cracks in it. This is the lime stabilized layer, which is very solid. Here are the resilient modulus properties. Now, you know what a resilient modulus is, of course. That's when we take, that's one of our primary tools, pieces of information that we use for pavement design. And what we do with that is we apply a deviatoric pressure, cyclic pressure that simulates moving trucks. And we do that under a certain level of confinement that mimics what happens in the field. So the idea there is to look at the ratio of the applied stress to the strain that that stress causes. And so therefore a high resilient modulus is a stiffer material. It does a better job of distributing stresses and protecting the underlying layers. It's a very important component of the pavement structure. So we want a higher modulus. The blue columns here represent the modulus of this natural clay soil. And you can see that at optimum moisture content, the modulus is about 12,000 psi, which is not bad. Not too bad. If you use FPS 21 or use acetone 93 or whatever you use, that's not a great modulus, but not real bad. But what happens when it gets near saturation, when you're 15 percentage points above optimum? What's optimum? Probably 80% saturation. If I'm 15 percentage points above, I'm over 95% saturation. When I get to that point, my modulus has dropped to 1,500 psi. So almost a tenfold, almost an order of magnitude drop. The calcium saturated soil has a modulus of about 32,000, and then when it's saturated, drops to maybe 26. So I have drastically improved the engineering properties of that soil by the saturation with calcium. And in addition, when I add a lime-based material, whether it be hydrated lime, quicklime, or Portland cement, that high pH is going to solubilize the silica and the alumina and make it reactive with the calcium to do some pozzolanic bonding of the materials, and that improves the surface chemistry and the strength as well. So calcium-based stabilizers have been around a long time. They have been extremely effective when used properly in Texas. Now I want to talk just for a second, to illustrate some of the soil basics, if I can have enough time to get here. And I want to talk about a different type of a non-traditional stabilizer. And many of you have encountered some of these stabilizers where you inject a liquid into the soil. The liquid permeates into the cracks and actually diffuses into the soil itself. And generally this liquid is an acidic-based material. It's an acid, it's almost all hydrochloric acid. I'm sorry, sulfuric acid, dominated by sulfuric acid. It has some oils in it too. And the question is, does that really do anything? Well, we can use our soil basics to help us understand whether it does or not. And I thought I would just show you. I'm going to go over that one. This is Xray diffraction. And Xray diffraction is just a tool that allows us to determine what types of minerals are there or present. And I'm not going to bore you with the details of the Xray diffraction if you just bear with me a second, but this is the Xray diffraction of smectite, the red. And these peaks along the way identify that that is smectite. They identify the despacing among the particles, and they tell us that's smectite. If I come down here and with this sodium saturated montmorillonite or smectite, and we know if it's sodium saturated, it's really got a great swell potential. If I put in a 1 to 20 solution of this oil, this acidic oil, and inject it or react it with the soil, then we see these peaks diminish. They're not gone, but they diminish to a certain level. And then if we put it at 1-to-1, fully concentrated, we obliterate all those peaks. So we've actually destroyed the clay mineral by adding that sulfuric acid. So it does do something. But generally, it is added at a ratio of something like 1-to-200, 1-to-300. So you got to get it to a pretty high ratio for it to be reactive. The point here is simply this. The point is that we can use some basic tools, and one of the most basic tool, which doesn't sound all that basic, but it's available at your TxDOT labs and your experts use it all the time, is Xray diffraction. Xray diffraction, it can really tell us an awful lot about the nature of the minerals, and it can tell us whether some type of a stabilizer is actually working. So right here, if we've obliterated these peaks, then what we've done is we've attacked that clay structure. Now I wanted to show you this real quickly because this was our hypothesis on what happened with these acidic oils. So this is just a simplistic representation of the clay structure. Remember, we've got these little tetrahedra with the peaks pointing down. We've got the tetrahedral structures with the peaks pointing up, and in between it we've got the aluminum octahedral layer. So that's our basic clay structure. Here's another one down here, and they're linked together by some type of a positively charged atom, either calcium or sodium. And over on the right-hand side, we thought that the clay or the acid would be solubilizing primarily this aluminum layer because at very low pHs the aluminum layer breaks apart. So our actual representation was that ultimately the aluminum layer would release the aluminum. It would form an aluminum hydroxyl interlayer which would bond these together and keep them from swelling because it does diminish swell potential. And then ultimately it would, but by the release of aluminum, it would diminish the integrity of those aluminum octahedral interlayers, and therefore the silica layers would also break apart. So this was our hypothesis going in, and this pretty much proved that that was going to happen. And the phase diagram that I skipped over because it's a little bit complex also helps us understand that that process is going on. So the point here is not all the complexity of the method of evaluating the soil. The important point here is by understanding what the structure of the clay looks like. It's a layered aluminate silicate structure, and the nature of the charged system and the way it absorbs water and other ions in there helps us understand whether or not these products are going to actually work. Now here is another test that Dr. Litton has done a lot of work over the years on, and that is looking at the soil suction method of evaluating shrink swell potential. And he uses a parameter that's this modulus here, which is actually the gamma sub H, and what it is the volumetric swell or the volumetric strain. You've got the change in volume over the initial volume, so that's volumetric strain, and this is the change in suction. So when I apply a high suction, I'm sucking, there's a lot of potential to suck that water out of the interstitial layers. When the suction is low, then the relative humidity is high and there's very little suction potential. So that's a change in suction. Now here is a curve that shows you this is matrix suction and this is volume. So the natural soil here is in blue. The black curve represents the soil that is treated with this acidic stabilizer. And over here on the right-hand side, you can see this modulus, which is the representative of the volumetric strain divided by the change in suction over different suction levels. And this is an excellent way to evaluate whether or not these stabilizers would actually work and change the properties of your soils. Would they make them more volumetrically stable? You can get these values through what we call a pressure plate test. It's a fairly cheap test to run, and it takes a little bit of experience, but once you have got it nailed, it's a very good tool. And what you see here is that the value of the gamma sub H, which is this swell modulus, if you will, is pretty much cut in half by the addition of that acidic stabilizer. So that's a fairly practical way to show that it may work. Why are those important? Well, I think those are important because the active zone, the active zone for swelling in many of our soils here reaches, as the TxDOT manual says, about 15 feet. Now, there's some controversy over how that is derived, but it varies from maybe 7 or 8 feet down to around 15 feet, depending on where you are. So if you stabilize the upper maybe 30 millimeters, 12 inches with lime or cement, or lime fly ash, cement fly ash, which does an excellent job, but you're not getting all the way down into that active zone that where you may need to get. So the injection of something into those deeper layers is a good option if it works. Water may work, and water will hydrate it and reduce the swell potential, but does water actually, is it a durable fix? I won't say permanent, but is it a durable fix? Well, it may be under the pavement where it's protected from movement, but at the edges, there's probably a lot of fluctuation with just water. So if you can add something in there that will actually change the properties of the clay chemically and stabilize those inner layers, it might be a lot more effective. Please let me know when I'm out of time, Richard or whoever. So here are some other illustrations of the property changes with some of those stabilizers. The natural soil in this case is the red. This is resilient modulus, and this is over moisture content. The blue is the lime-treated clay, and the black is the acid-treated material. So it's not as effective as the lime, but it does change the engineering properties to some level as well. The last thing I wanted to talk about with you is a new stabilizer for soils that we're working on, and it's a polymer-based stabilizer. It's quite effective in the sense that it only takes about 1.5% to 2% of the polymer, although it's expensive, but it takes much less of it to stabilize these soils. So we thought we would look at these different types of polymers. The polymers that we look at we combine a polymer that has negative charges on it and a polymer that has positive charges on it to form what we call a polyelectrolyte complex. And the idea here is that the different charge systems will interact with the different components of the clay, whether they might have positive or negative charges, and it be attracted to them and stabilize them. And we try to make the center part of the structure hydrophobic so that it will not sorb water. It will actually repel water. That was our mission. That's what we worked on. And what we found out is that by making this center core hydrophobic so that it would not attract water, and being able to attract the edges of the clay structure with the either positive or negative charges of the polymer, we can link it together and improve its strength and also make it resistant to the effects of moisture. So this is the early version of the polymer. It worked very well when it was dry, but you put it in water and it fell apart because it attracted water. Working on it to make it hydrophobic, resistant to water, but yet attractive to the soil particles, we were able to make it to do that, improve that functionality. I wanted to show you a couple of other slides that illustrate the effectiveness of that polymer. This is kind of a busy slide, but this is resilient modulus. This is a limestone soil not a clay, just a limestone or calcareous-based soil, almost an aggregate. And this is the resilient modulus untreated. That is the resilient modulus of that limestone with cement. And this is the resilient modulus with the polymer. So you can see it does have engineering properties that are competitive. This is something called fracture toughness. Now this is very interesting because fracture toughness is the, I need to stop here. Fracture toughness is the ability to resist fracture and to provide good fatigue resistance. And what you see here, and this will be my last slide, is the untreated stabilized, or the untreated limestone. This would be the limestone with cement. This is the limestone with 2% of the polymer, and this is the limestone with cement and the polymer. And you can see that the fracture toughness is dramatically improved. And that's because the polymer tends to dissipate energy as it coils and kinks and so forth, and improves the fracture toughness. Well, anyway, just as a closing remark, what I've tried to do here today is just to show you a little bit of the basics, primarily of clays, and how that basic understanding can help us also get a good feel on what additives might improve it and how that improvement might take place. So thank you for your attention.